Okay. This, of course, is not new to you, I'm sure. Systems of unit, and depends on really the profession you're in. But in this course, we'll use really two systems: the metric and the English system. Now, these systems are typically based upon what we call fundamental quantities. And that is the definition of whatever we're trying to measure. And we start and there are actually 7 major fundamental quantities, and the ones that we will use most, of course, is length, weight, and time. But you also have fundamental units of mass referring essentially to what we call the mole concept, or molar mass, which is a very specific to the chemistry. You have things like lumens, which refers to light intensity, and you have sound intensity, or decibels, which is audio volume, so forth, like that. Then you have, in some cases, uh, you'll have volume. And if you do not have a volume listed in length, weight, length, width, and height, in that context, it is a fundamental. You have to establish what you mean in terms of volume, gallons or liters. Well, those are specific fundamental quantities that we define in terms of volume, and we apply those however many units we need to use. But from that, we want to develop our units that really revolve around length, weight, and time. Okay. In working with any measurement, there are 3 things that make sense, that make the measurement make sense: define, standardize, and compare. Well, the definition of the unit is the fundamental quantity. And so we'll go fundamental quantity. We want to go length, weight, and of course time. And then we have the English system, and of course the metric. This would be MKS, what we call the MKS system, or SI system, Standard International Metric System, refer to it. But the length in English, of course, is the foot, and then we have the meter. Weight is the pound, and this is the kilogram. And then time for both systems is a second. Some people use SEC or whatever they want to use in that. Now, when we talk about these represent certain givens as far as what we call standards. Then, when we make a measurement, we compare it to these standards, and we know that numbers bigger than the standard have powers of 10 to them, and those that are fractions of the standard are powers of negative powers of 10. So what I want to do is build a little prefix table for you. Okay, it says comparing measurements through prefix values. Now, drawing a vertical line, give yourself some space, but right here in the kind of in the middle, right here, we're going to call that the standard. And so for we're working with length, of course, that'd be meters, and then actually you have to start with grams when working with the weight prefixes. but the standard does have a prefix. And of course, let me move that over, grams, and then seconds, right there. So for multiples of the standard, we'll have something like times 10 or times 100, and what up, say, times 1,000, and times 1,000,000. And they don't have any between those two, between 1,000 and 1,000,000. And then you come up here, I'm running out of room, 10 to the 9th, and then we have times 10 to the 12th, okay? So when we talk about meters, 10 meters, blocks, 100-meter blocks, 1,000-meter, or grams, we talk about 10 grams, 100 grams, 1,000 grams, and so forth. These are condensed into what we call prefixes. If it's 10, we use a prefix. I like to use capital letters on those numbers greater than the standard. Decameter or decagrams or decaseconds. That's a block of 10 meters, a block of 10 grams, a block of 10 seconds. And then you have hectometers. That's 100 meters, or hectograms, 100 grams, and so forth. 100 seconds. Kilo for 1,000, and kilograms is the standard for the SI system. But you have what's called CGS system, centimeter gram second. But at any rate, we're working mostly with the kilogram. Megameter is a million meters. Megagrams, million grams, and megaseconds is a million seconds, and so forth. Giga, a giga. Refer to that when you talk about storage in computers, gigabytes of storage and something like that, and 12 a tera. Same way, terabytes and so forth like that. So by taking those prefixes and attaching them to the standard, we're talking about a large block of those units. Now, when we go to fractions, we go to 1/10. So I'm going to put some of these 1/10, and then 1/100, and 1/1000, then 1,000,000th, minus 10 to the 6, 1/6. Yeah, 1/10 to the 6. We'll just stop at a billion on that one. Now, it's important that you also recognize these in terms of their powers of 10 or decimal fractions. Of course, this is a 0.10, 0.01, 0.001, and that, which also is 10 to the minus 1, and 10 to the minus 2, 10 to the minus 3, and this, of course, is 10 to the minus 6, and 10 to the minus 9. So when we attach a prefix to these, we want that prefix to reflect a fraction of the standard. And when we talk about 1/10 of the standard, we want to use a DECI, decile. Okay, and I use lowercase for those, just personal, there's no rule about that. I just use it. Okay, and centi, centimeter, as you remember from a metric ruler, is 1/100th of a meter, and millimeter, milli, and then micro is 1,000,000th, and nano is a billionth. So if you put the standard onto those prefixes, you certainly wind up with a fraction, or you're talking about or trying to describe a fraction of that standard. So this is kind of a useful little table. And try to use that. Looks like I might have missed it there. Everybody see that okay? As you already know, this is the process of converting one dimension to another dimension. Now, when we start talking about dimensional analysis, I break it down into really three categories of conversions: simple, multiple, and complex conversions. Now, simple conversions, and I'll use some examples in a second, are unit to unit, meters to feet, or miles to centimeters, or something of that relationship. Multiples deal with squares and cubes. Okay, going from cubic meters to cubic feet, and something like that. A complex conversion involves two fundamental quantities. One cannot be converted into the other. Pounds cannot be converted into a volume number of pounds per cubic feet or something like that. So you have to leave them in that format, and we call that a complex unit, or I use them in complex conversions. Okay, so we'll start with some examples of simple conversions. And most of you have had some experience with this, and you use the format you know are most comfortable with. I use time, sign, and lines and ratios and stuff like that. So the question is, how many centimeters equal 1.8 miles? Now that's kind of extreme, but the idea is I'm starting out with a question. Well, what are they asking for, and where are they going? Well, we're at miles and need to go to centimeters. Now, I attached to the exam a conversion factor table. Okay, starting over. We want to convert miles to centimeters. We want to get rid of miles, and we'll go to feet. And 5,280, and miles cancels out, and I'm going to get rid of feet, and go to inches, and they're 12 inches in foot. What I'm saying is, don't find yourself putting units down a conversion. 1 inch is 12 foot. That's not correct. So be cautious of how you string them out. I think you know what better than that, sure. So 12 inches a foot, so our feet go away. And I happen to know the conversion. Look on the sheet. I can get to centimeters, 2.54 centimeters an inch. Inches goes away, and so we have arrived at the appropriate units we wish to convert to. And so we collect all the numbers. So all the denominators will be 1, so I'm just going to go 1.8 times 5,280 times 12 times 2.54. Everything's going to come out in centimeters. Okay, so here's your calculator. All right. Now, you want to convert it to standard form, move your decimal. Times, and I move 5 places, times 10 to the 5th centimeters. And what I want to tell you here is, when deciding on significant figures, use the data, not the conversion factors. Use the data, not conversion factors. So the data given was convert 1.8 miles. Well, that's 2 sig figs. So your answer should be 2 sig figs in that. So that'd be 2.9 times 10 to the 5th centimeters would be the appropriate answer for that. So same with if you have to apply a constant, universal gas constant, for example, ideal gas law, 0.08206. Well, you don't use that, the numbers in that, or any constant for that matter. You use the data given, because that defines the experiment. Sig figs are experimental issues. Okay, so that's the idea of simple conversions, and there are worksheets online, and please practice these and apply due diligence to be able to work toward those endpoints. Okay, multiple conversions. Okay, so we want to convert, say, squares and or cubes. Question? Okay. Anyway, make up something. Okay. How many square feet equal 2.85 times 10 to the third square centimeters? Something of that nature. Okay. Now, the rule that I give people is make this a simple conversion and then square your conversion factor. Now, the data given here is already in square units. You hear what I said? The data is already in square units. All right? So you want to put the conversion factors, the series of conversion factors, in simple form first, unit to unit, and then square them. I'll show you. So we're going from centimeters to feet. So this would be equal to, let's go to, let me rewrite it, 2.85 times 10 to the third centimeters squared times, okay, I'm going to centimeters to feet. Centimeters goes to inches, and then inches goes to feet. See that? I'm using simple conversions first. 2.54 centimeters in an inch, and 12 inches in 1 foot. Now, once you get there, put parentheses around your conversion factors, and you square them. That's a square. So you already know how to do simple conversions. All you do is just bracket the conversion factors and square them. Okay? And so this would be, and I string this out for academic reasons. No, centimeters will drop out, inches will drop out, and you're left in square feet. So throw out all the numbers, I mean the units, and just keep the numbers. Okay, so this is 1 over 2.54 squared. 1 times 1 is 1, obviously. And that's 1 over 12 squared, and then everything is going to come out in square feet, like that. So, stringing this out, okay, this will be 6.4516, and 144, divided into 2.85, 10 to the third, like that, and that's square feet, like that. So, 3.06, make that a little clearer up. 3.0677. Looking through our values, looks like 3 sig figs, so 3.07 square feet would be the appropriate number. Now the issue here is the squaring of the units, conversion factors. The data point is already squared, so don't try to double up on that and square it. So these are combinations of, that says fundamental quantities out here on the end, okay? Say you're given 63.85 pounds per cubic feet. Convert to grams per cubic centimeter. Okay. Now, when working with grams, that's a simple conversion. But when you're working with your conversion from feet to cubic centimeters, you do the same way we just talked to you. Work with them in terms of simple conversions, then cube, in this case, the conversion factors. So it doesn't matter which one you start with. You start with pounds and make that conversion. When you finish it, then you turn around and do the feet. So how many grams per cubic centimeter is equal to 63.85 pounds per cubic feet? So I want to start with pounds and go to grams. I do know there are 454 grams per 1 pound, so that completes that little conversion very quickly, right there. Okay, then we want to convert the feet to cubic centimeters. Now do it as this is on the denominator side of the ratio. So I want to start here, feet, and then inches, and then inches to centimeters. So we do simple conversions first. 1 foot, 12 inches, 1 inch, 2.54 centimeters, and then go back, and in this case you'll cube each of the conversion factors, and then run your computation from there. So that would be 63.85, 454 divided by 12 cubed, and 2.54 cubed, and that's going to come out in, get my units canceled, grams, inches, okay, that'd be grams per cubic centimeter. Okay, 1.023698. And we look back at the original data, which is the 63.85 and 4 sig figs. So we went around to that position right there. So this would go to 1.024 grams per cubic centimeter. We'd have to move that up one to the next higher digit. So in that. So that is the protocol for fundamental conversions, and hopefully that makes sense. Now, we're using common SI units, but you have conversions like this for moles, particle numbers, and so there's always an equivalent relationship between something. But the procedure and the protocols are always the same. You want to go from one dimension to another, you try to cancel them out until you reach the dimension you need. I think you understand that. Actually, this is percentage parts per million, ppm, and parts per billion. Like that. They're all based on the same definition. Part over total times some big number. Well, percentages times 100, millions times a million, and billions times a billion. So when we talk about percentage, by definition, it's a part over total times 100. And we typically tag that with percentage. We're talking about parts per million. It's same part over total times 10 to the 6. And we tag that with ppm. And parts per billion, ppbs, part over total times 10 to the 9th, ppb. Like that. So for definitions, those are, as you see, very similar, except for the multiple that's used at the end of the diagram. Percent sodium chloride is the mass of your sodium chloride over the mass of solution, of course, times 100%. Now, one issue that students sometimes miss is the mass of this solution. And look at the problem itself. 250 milliliters is not the solution weight. Solution is the combination of solute and solvent. Solute is 25 grams, and the solvent is 250 grams. So this is 25 grams of salt plus 250 grams of water, which gives the denominator to be 275 grams total. Right there. So now I could have rewritten the problem, and sometimes it shows up, Given aqueous solution that contains 25 grams of sodium chloride and 250 grams of solution. You mentally say, oh, solution is a combination, so that is what I divide by, 250. So you want to separate definitions of what you're working with and be sure you apply them right. And this is one case that pops up. Okay, so please make note. So this percentage problem then, sodium chloride is 25 grams over 275 grams, which drop out, multiply times 100%. Which is 9.0909%. And this rounds off to a 9.1% because the data point here is the least number of significant figures. Right there, 25 grams, that's 2 sig figs in that. Now, if we're working with parts per million and parts per billion, it's the same process, okay, and that you part over total, but you want to convert it into parts per million. When you see a number given in percent, 0.00321%, well, what does that mean? If you have that number, then, and you need to incorporate it into a calculation, transfer that into parts per hundredweight. That, like in grams or it doesn't matter. It's parts per hundredweight. So this means of 0.00321 per hundredweight. Over 100. It's always over 100. 0.00321 grams per 100 grams of mix, whatever total weight. Or it's 0.00321 tons per 100 tons of mix in that. Okay? This is what you should convert to, regardless. It doesn't matter what the units are, because it's going to be in a percentage ratio anyway. Then you want to go to parts per million, just simply multiply times 10 to the 6 and tag it with ppm. That's the simplest way to get these. So when you see a percentage, think of it in terms of that over 100. And so this would be 0.00321 over 10 squared times 10 to the 6, just to hit some high points or hit some nerves or something. So this 10 squared and 10 sixths would go 10 to the 4th, and then your numerator would be 3.21 times 10 to the minus 3, and then times 10 to the minus 2 times 10 to the 6. Everything comes out in ppm. There we go. 3.21, 345, add back 6, times 10 to the first power, ppm, and that looks like about 32.1 parts per million in that case. Well, if you're working to a parts per billion, you set it up the same way, except you'll put a 10 to the 9th over here. And so it would be 0.00321% goes to 0.00321 over 100, or 10 squared, times 10 to the 9th parts per billion, and then you work it out to the appropriate standard form, as you would. And that's 3 more places. It'd be, I think, about 32,100. So that would be, if I'm not mistaken. So there's 3 more, got 3 more zeros on there. Anyway, so the simplicity of this is you need to know that it's part over total times whatever value you're trying to go to. Percent is always times 100. Million times 10 to the 6, 10 to the 9th is billions. Okay, so here's another issue. Given a concentration of an element, I just made up something, is 275 parts per million. 275 parts per million. What is this in percentage? Same idea. How do you interpret parts per million? It's parts over 10 to the 6, right? And if you go to percentage, we always multiply times what? 100. That's what you're saying. Okay, so percent element is equal to 275 whatevers over 10 to the 6. That's what that means. And then if you go to percentage, times 100%, tag it with a percentage. So what I'm trying to get you to focus on is, well, what is the percentage? Well, parts per 100 weight times whatever you're going to. And parts per million or parts per billion, that would be over 10 to the 9 times 100 to get to percentage in that case also. Or if you're going from parts per million to parts per billion, is this over 10 to the 6 times 10 to the 9. And so you make your adjustments always part over total times 100. And so this would be 10 squared. And so that's the 2.75 times 10 squared there. And so that would be 6 to the minus 4. And so that'd be 2.75 times 10 to the minus 2%. Sometimes when you see a percentage written, you'll see a W/W, or you'll see a weight percent. That means the ratio is based upon mass over mass values. If you see a V over V value percentage, that means it's based on volume percent. Sometimes you go to buy isopropyl alcohol at the pharmacy, it's 30% isopropyl alcohol. That means 30 milliliters of pure alcohol and 70% water is solution. And so it'd be a V/V. Then you have V/M, or mass, V/M ratios, percentage sometimes. So, but just want to emphasize what these terms and units will show up look like. Temperature conversions, of course, you're familiar with the Fahrenheit. Celsius, and absolute or Kelvin scale. Now, Fahrenheit and Celsius, just to make a trivial point, but it's important, those carry the superscript little circle, but Kelvin does not. It's an absolute number. Anyway, the object here is to be able to go from Fahrenheit to Celsius to Kelvin and back. So how do we do that? Well, we can use the conversion equations. Degrees Fahrenheit is always 9/5 degrees C plus 32. Degrees Celsius is 5/9 degrees F minus 32. But you have to put parentheses around that. So the C looks like a parenthesis. That's the way I remember it. And your Kelvin value is 273 plus whatever your Celsius value is. And so the Fahrenheit Celsius conversions I want to derive using the point slope method here. The point slope method uses y minus y prime to equal change in y over change in x, x minus x prime is the empirical relationship. Well, when we translate this relationship into the graphic that I've written up here, we have degrees Fahrenheit minus whatever a given value is. Now, I'm using the freezing point and the boiling points of water as the corresponding points in here. So starting with Fahrenheit, I'm going to use this freezing point because it got a 0 in it, and it makes it this side of the calculation a lot easier. So I'm going to use the freezing point number, so that's minus 32 right there, okay, for the Fahrenheit side. And then you have change in Y, which is 212 minus 32 divided by 100 minus 0. There's your slope. And then you have degrees Celsius minus 0. And so we want to simplify that, and that would be 180 over 100 degrees C, like that, and that's 9/5. See that? 9/5 degrees C. Okay, so we have the Fahrenheit minus, I'm going to move it down just a little bit. I'm going to bracket this off. See, like that. So if I solve this for degrees C, I divide both sides by 9/5, right? And so it have 5 over 9 degrees F minus 32, which was one of the equations that we showed you. Or if I solve for degrees Fahrenheit, I would go to, solve for Fahrenheit, then I would add 32 to both sides, and that would have 9 over 5 degrees C plus 32. And so you see, it's pretty straightforward derivation here in terms of those. Now, you won't have to do that on exam day, but you will have to make conversions. And some of the calculators already do that for you. But anyway. This is the standard form of what we call the point slope analysis. And so y-axis, x-axis, all I'm doing is taking a value for one of the points, in this case the freezing point. And the prime numbers, y prime, of course that's the xy here, and your variable would be y and x, translate into Fahrenheit and Celsius, minus 0 degrees. Well, we'll put degrees up here, that's fine. Then all I'm doing is simplifying this, like C minus 0 turns into a C, 212 minus 32 is 180, 100, and that reduces to 9/5 C. That's all it does. Okay, then what I did is I took this and this, right here, and in one case I solved for C, divide both sides by 9/5. And this one, F, all I had, I had 32 to both sides. And that's all I did. I didn't mean to get out of hand and complicated. Your job is simply going to be just apply the equations and make a conversion. And that's the long and short of that. But I always try to show where these equations come from, because many people use them, but they never see where it actually comes from. Does that kind of help? Sorry about my handicap. Okay. Now, the objective here is to explain what the units of energy are and where they come from fundamentally, and establish a couple of conversion factors. If you look on the handout I gave you, on that right column, you will see an energy conversion, calories and joules relationship, 4.184 joules equals 1 calorie. Now, if you had joules, you can convert to calories, or if you had calories, you can convert to joules using the appropriate ratio, just like we did with the linear conversions and simple conversions that we did earlier. Energy, according to our physics friends, is the capacity to do work. That's the fundamental. Okay? Work, by definition, is a force acting over a distance, or force times a distance. Okay. Well, also from our physics friends, it turns out that force is mass times acceleration. And then again times distance. Like that. Well, if we apply the SI units to that, we have kilograms for the mass times meters per second squared is the fundamental for acceleration. That's the units of acceleration. And then times distance, which is in meters again. If we combine those, we get a complex unit that looks like this: kilogram meters squared. See, meters times meters gives you meters squared, divided by seconds squared. Well, that's definitely a cumbersome unit to use. Well, the chemical community and scientific community have changed this to the joule. So the units of joule, when we break it back to the SI system, is kilogram meter squared over second squared, like that. And so that's where that particular unit comes from. And it's a unit of energy or heat. Now, the other unit, and we want to relate to this, is the calorie. And we're going to come up with a conversion factor, basically, is what we're doing. I'm trying to show you where things come from. The calorie, lowercase c, is different from a nutritional calorie in that a nutritional calorie represents 1,000 of these scientific calories, as I call them. Okay? Now, the calorie is a specific number of referring to the amount of heat gained or absorbed. And the basic definition is 1 calorie, by definition, is the amount of heat energy needed to raise the temperature of 1 gram of water, pure water, (1.000 degrees Celsius). That's the textbook definition of a calorie. The relationship between the calories and the joules is what we're interested in making conversions. That is 1 calorie, lowercase calorie, is equal to 4.184 joules. Kilojoule is 1,000 times that. Anyway, this is the main thrust of what I'm trying to share with you. I'm trying to show you where it comes from, what their basic definitions are. But when it all boils down, you're not going to have to repeat all this as much as this. Now, later on, when we cover thermochemistry, we'll get into that a little more in depth. But this is the primary objective and is used just like the other conversion factors. Say you're given reaction gives 91.8 kilojoules of energy. Convert, or what is this? In calories. That's all I get to. That is, how many calories is equal to 91.8 kilojoules. And again, we want to go from kilojoule to calorie, but the relationship is joules calories, not kilojoules calories. So we want to go kilojoules to joules, and so there's 1,000 joules per 1 kilojoule. So that will make that conversion. And then we can go to calories. We have 4.184 joules, 1 calorie. And so joules will then drop out. And we now have 91.8 times 1,000 over 4.184. And that'll be calories. Calculator answer for you. So again, we only use data for defining the number of significant figures. So we need 3 sig figs. So we'd round it to this position, and everything else would be non-significant figures, zeros. So we can put this in as 21900 counts is the appropriate answer to that.